Long Now Boston Conversation series. As Jennifer noted, Dr. Elvis is senior astrophysicist at the Harvard-Smithsonian Center for Astrophysics. In addition to his significant contributions to the science of deep space objects, Dr. Elvis has a passion for near-Earth objects and the opportunities they offer for future space exploration and development. Dr. Elvis has published over 400 journal papers and is one of the 250 most highly cited researchers in astronomy and space physics. So Martin, it's great to see you tonight.
Good to be here.
Yeah, and are you ready to take us all into deep space again?
Sure. Shall I share my screen?
Not yet. Some of you may remember Martin's fantastic talk to us in March 2018 on asteroid futures. That was a spellbinding romp through the solar system and some provocative speculations on the long-term potential for the industrialization of space. So in June of 2021, Martin published Asteroids, How Love, Fear, and Greed Will Determine Our Future in Space. This is significantly expanded on the Long Now Boston talk 3 years before, and it's a fascinating and well-crafted read. And to thank all of you for coming tonight, we're going to offer an opportunity to win a hard copy of Martin's book as a door prize. Some of you may know how this works if you've been to some of our prior events where we featured a book. The prize will be given for the first correct answer to the following question. Please post your answers as quickly as you can in the chat once we ask the question. And Mary, if you could track and identify the winner, we'll take that data down and we'll be able to get the book off to you. So here's the question. What is likely to be the first material commercially mined from asteroids due to its very high value in space? So that's the question, the first material to be mined. And Martin, you covered this topic. We don't want to give oh, somebody got it.
Yep.
How about that? Look at that. So yeah. And the answer is, Martin, what's the answer? What's the most likely?
Right now, everybody is trying to mine water, but I see other people have put in iron, and actually,
it was a close second.
That's a good guess.
Yeah.
I think that's going to be the second thing.
Yeah, and I was astounded that water would be, it's not the kind of thing you normally associate with asteroids or space or anything else. But if
take this glass of water to space costs you many $1,000s. So if you can find it from space, then you can avoid that cost. So
yeah. So Mary, we have a winner, and I think with that, Martin, why don't you do your screen share and take over the presentation?
Okay. There. Can you see that?
Yep. Thank you.
Beautiful.
Terrific. Okay, I'm going to talk about this strange object, Oumuamua, which is a Hawaiian word, which has been championed as maybe the first alien craft to be detected as it goes through our solar system. And this is not science fiction. This is a serious proposal, but many people reject it rather rapidly, and I got annoyed by that. So I wrote an actual book, paper, which is published now in the International Journal of Astrobiology, that looks at what would happen if it really were. What should we do, right? Apart from panic, right? So let me see, hang on. Now I can't move my, there we go, good. So first, what is Oumuamua? It's got this strange name, 1I 2017 U1. 1I stands for the first interstellar object. It was found in 2017. And it was discovered by this telescope on top of a mountain, Haleakala in Hawaii, the Pan-STARRS telescope, which was the first telescope really able to find such objects, because it's bigger than the other telescopes that have been used to search for asteroids and comets, and it covers a very wide piece of the sky, big field of view, as we say. And so it can cover the whole sky much more rapidly and deeply than previous telescopes. So it was actually the first chance we had to discover such an object. The name Oumuamua stands for scout in Hawaiian. As you see here, O means reach out for, and Mua means the first. And Muamua means it's really the first. It's emphatic. That's all. That's the reason it's doubled. Now, unfortunately, Oumuamua was only found on its way out of the solar system because in that case, it was on the dark side, the night sky side of the Earth, it happened to be. And that meant we only had 80 days to study it with pretty much every telescope we could throw at it. And that led to it meant we had very little information about it. It was already pretty darn faint. After 80 days, nothing could see it, even the Hubble Space Telescope. But the key thing about it was that it was on a hyperbolic orbit, meaning it was in no way bound to the solar system. It had actually gone fairly close to Earth, but we didn't see it then, and then it zipped by and it was picked up by pan-stars and then on its way out. So the fact it's a hyperbolic orbit means it's interstellar. There's no way out. It has an ellipticity of 1.2 if you want to get technical. So what do we know about it? Well, we got colors, and it turns out to be rather red. It's about 100 meters in size, sort of maybe a couple of times that. Well, the reason we don't know how big it is exactly is we only have optical measurements, visible light measurements, which are reflected sunlight. And the trouble is, the bigger something is, the more sunlight it reflects. But the darker it is, the less it reflects. And there's a big range in how reflective the asteroids are, from maybe a quarter of the light impinging on it to less than 1%. So something fairly shiny down to something darker than fresh asphalt. So what we do know is we were able to track how bright it was, and it changed in brightness a lot. And this is a series of points plotting, showing how bright these things are, this thing was. And you can see that it comes up and down fairly regularly, about every 8 hours. But if you look closely, the little white dots fit the little dashed line fits the early data, but doesn't fit the later data. So that means it's tumbling. It's not simply rotating smoothly, it's doing something like that. Okay, and that's unusual. And as it tumbles, it gets brighter and fainter and fainter by a factor of 10. Which is enormous. That means the reason it would get fainter and brighter is most likely because when it's bright, it's more face onto us, and then when it's dark, it's edge onto us. So it's a very long, elongated or flattened object. So there were the first cartoons to come out of it showed it like a cigar. A later one, just as plausible, more like a pancake, not slightly resembling the Millennium Falcon, if you ask me. So they invented that. So that's all very, very nice. And we naturally would think, well, this is the first interstellar asteroid to come through our solar system. They're red, they tumble. Asteroids in general, so why not one from another solar system? Whoops, something's happened. There we go. The real puzzle is why it accelerated on its way out of the solar system. It was going at a certain speed, and then you'd expect it to slow down, if anything, as the sun's gravity pulls on it, but instead it accelerated. And basic physics tells us if you get a large acceleration, it's because you've got a small mass or a large force acting on it. This is Newton's second law of motion. So we can see what force can we find that might be doing this. So comets, when they come by the sun, get warmed up on the sun-facing side. That causes volatile material like carbon monoxide to burst out of the comet's surface and act like a rocket, pushing the comet in the opposite direction. But there were no gases that we could detect, even though we looked carefully with an infrared telescope that's very sensitive to these. So maybe You could say, well, it's some other kind of gas that we didn't look for and we are in the short time available, maybe. Or if it's not an acceleration due to some gas escaping, maybe it's radiation pressure from the sun. And that actually fits the detailed shape of the acceleration, which reduced as it went further away from the sun, as a 1/r² law, if you follow that kind of thing. So that was nice, but to use starlight, sunlight has very weak pressure. It does have radiation, but the radiation from the sun does exert a pressure on anything, but it's a very weak one. That means you have to have a very big area and a very small mass to intercept a lot of sunlight, but and only have to accelerate a small amount of mass. And the number turns out to be 100,000th the density of water to make that kind of acceleration possible. So that's pretty strange. Whatever is doing this is something we've never seen before. And maybe for an interstellar object, that's not strange, that we'd expect strange things, but what exactly strange things? So astronomers immediately got to work suggesting all sorts of possibilities. Yeah, there we go. There were various kinds of gas that we wouldn't have found that something could be made of. Molecular hydrogen ice, molecular nitrogen ice. These are plausible sounding materials. The other possibility is some kind of very fluffy material, so-called fractal aggregate that could get very low density, and there's several ideas of where they all come from. And you can see the whole lot of different people were involved in this. But Avi Loeb and his collaborators, in each case, and I've written a couple of them down on the slides here, found a real problem with each of these astrophysical explanations. And for instance, that it might be, if it's nitrogen gas, which works very well, then as a material, but where do you get enough nitrogen? And it's very hard to find that much nitrogen. Or if it was made of hydrogen, in fact, you'd find it would evaporate rather too quickly to have made it to the sun across the interstellar distance. So he had good arguments, and the normal course of events would be that people then write other papers saying, no, have you forgot this or that? And I found another way of doing it, but that isn't really what happened. What Avi said, having exhausted all the possibilities, he thought, maybe it's an alien craft, because that would make sense. And he could claim that it's like the Sherlock Holmes thing of eliminating the improbable. Then you have to you're left with your very what is the Sherlock Holmes thing? Never mind. That you have to accept the outlandish answer if all the less outlandish ones don't work. So that led to two camps turning up, Avi and Shmuel Bialy and Amir Siraj on one side saying it's aliens, effectively. And on the other side, a whole bunch of commentators saying, no, it's not. And the two of them who made particularly, I think, poor responses on that side were Jonathan Katz and Ethan Siegel. And if you see the recorded version of this, you can look at those links, which look a bit imposing to find now. So Avi, of course, responded, yes, it is. And I've written a book to prove it. And that was a best-selling book. And I think you heard from Avi a while ago on this topic. But the whole thing annoyed me because it was no longer being worked on as a scientific problem. It became an emotional thing, I think, for many scientists. Whether Avi sometimes got a little over the top on it, but mostly I think he stayed within perfectly reasonable scientific bounds, especially in his published papers, rather than, say, the popular press articles. So why did he think an alien craft was a good idea? Because he's been thinking about light sails a lot, which naturally have large area and low mass, which is what you need for the to make Oumuamua accelerate under light pressure from the sun. It would be a few hundred meters across. It would be less than 1 millimeter thick. That's challenging to us. but perhaps not so challenging to an alien civilization. The total mass of this thing would be less than a ton. A metric ton and a US ton are about the same within 10%, so don't worry about it, the metric numbers, if you're not comfortable with them. So what I thought one should do is ask the question, okay, suppose it's an alien craft, what would that imply? And I think one of the worries that led to this sort of knee-jerk reaction from other astronomers is the feeling that if you say it's aliens, that's a dead end. It's like, okay, aliens can do anything, right? It stops being science. We just start speculating. And Imre Lakatos, a historian and philosopher of science way back in the 1970s, found that when scientists get a good research idea, a research program, when they can see that research can lead somewhere or use their special skills that they can apply, then they will take up the project and start working on it because they have something to work with. If you just say aliens, that doesn't help you at all. So I think, in fact, there are avenues to pursue that are promising, and I'm going to outline them here. So one is, there's only two options, right? Either it was under control or it was a derelict, not controlled. And so those two have different implications, and you can look at them. And I'll go through the argument by what's coming up. And the third thing is, this thing has to have been in interstellar space for a long time. It makes the 10,000-year timescale of the Long Now Foundation seem rather short. So there's a real problem of reliability engineering. Something I've been reading about just for this paper, but it's a big field in engineering. If you want something to last a certain length of time, how do you make sure that's going to happen? Now, I had to adopt a couple of ground rules to make this a useful exercise. First, whatever the prediction is, whatever the branch of the possible situations you want to choose, it has to end up with some kind of testable prediction, because otherwise you're just talking, right? If it's not making any kind of prediction, it's not really science. And secondly, it must use known physics. Another tendency is to say, well, aliens, they're 1 billion years older than us. They can do anything. They can have wormholes. They can go, they can have materials that are stronger than we could possibly imagine. And that's just not going to work either, because if we assume that, then we can't constrain the problem at all. And in fact, we know an awful lot of physics now, and they're not going to use elements that we don't have. They might, for instance, we know all the elements. They might find compounds and molecules that we haven't produced yet. That's possible, but there are fundamental limits that even aliens can't get around. And so we're going to use those. Okay, so let's look at the first option. It's a derelict. It's not controlled, right? One reason to think this might be the case is that Oumuamua was not moving relative to other nearby stars. We basically ran into it. The solar system ran into Oumuamua. So that means we have no hint as to which star it came from. It wasn't clearly coming from a direction where 100,000 years ago there was another star. We know all the nearby stars, we know how they move, and there just isn't one. There's just no clue from its motion where it was coming from. So that, in this case, if we say, okay, we don't know where it's coming from, but it's an alien ship, that suggests it's something kind of strange. It could be the message in a bottle scenario, in which case the message is simply, we exist, right? But we aren't going to tell you where we're from because we're worried that you might do something nasty to us. And if you've read Cixin Liu's trilogy, starting with the three-body problem, then particularly in the Dark Forest, things get pretty nasty for humanity when aliens find out who we are and that we are there. So it could be a new kind of message. METI is messaging extraterrestrial intelligence, where we send out a message to into the space, into either to a targeted star or all over the sky. This would be messaging by an extraterrestrial intelligence, and it would be anonymous, and they deliberately so. They would deliberately be hiding their location from us, which may be a smart thing to do. And the test would be, you go there, go to Oumuamua, and there should be nothing like the Pioneer 10 and 11 plaque, which was designed to show where we were. Those little rays coming out of a central point there on the left, they are the code for the nearest pulsars to our solar system, and their directions and their pulse periods and pulse shapes. And so astronomers, alien astronomers, could work out where we are by finding the pulsars and using that to find out, use this as a map. So we'd again have to go check Oumuamua itself to see if there was anything up close, to see if there's any kind of marks that might be telling us where it came from. Another version of messaging by extraterrestrial intelligence would be accidental METI. So we've sent several upper stages on solar system escape trajectories. We've sent 5 missions, that spacecraft that are escaping the solar system, right? The Pioneers 10 and 11, Voyager 1 and 2, which are the most famous, and now the New Horizons mission, which has passed Pluto and is now out in the Kuiper belt, beyond Neptune and Pluto. But not only did the spacecraft get to escape the solar system, so did their much larger upper stages, like the one on the left in the Centaur upper stage. That was very much the kind that was used for most of these. Could it be that aliens are producing this same kind of interstellar trash from their space program, which we could call accidental METI? So then you have to say, yes, but why would it be in this very strange form of very thin, very large, low mass sails? And the answer could be very much inspired by Project Starshot. This is where Avi is involved in this. The idea is to send very tiny, few gram spacecraft with cameras and a transmitter out to Alpha Centauri and zip past any planets that are there and send us back images. And they would be accelerated. There'd be solar sails, but they would be accelerated not by the sun, but by laser beams. And if you've got to travel around a solar system, this is a very good way of doing it, because you're not carrying any fuel with you. The fuel comes from the rocket comes from is the laser hitting you, the sail. So that's a very efficient way to have a space travel network. But it could lead maybe to thousands, millions, trillions, perhaps, of waste solar sails that just keep going when the passengers on board drop off at their destination. So how would we test that? Well, there could be brief laser flashes from nearby stars if they miss occasionally. Might be if the rate at which these are being sent out could be is very high, and many to produce little. Or because of the scale of this, it would have to be very large numbers. So they would be mining, they'd be using their whole solar system, perhaps mining their asteroid belt if they have one. And that would lead to piles of dust. They're not very careful environmentalists, obviously, if they're sending all this junk into interstellar space. There'd be leftovers from the mining operation, which we would see probably as an infrared excess of light from old stars where normally we don't see any such thing. So that would be a bit of a clue. Or, of course, we could once again send a spacecraft to Oumuamua to take a look and see if they look like this kind of solar sail. If it's uncontrolled, then if it's controlled, they target us, and then there's only has to be one of them, right? You'd think, or very few. But if they're uncontrolled, they have to be filling a lot of space for us to accidentally run into one. Oops, I've got lost somewhere. Okay. You can work out from how much space the Pan-STARRS telescope could view at a given size of asteroid, stellar asteroid, how many of them would have to be there for us to have a decent chance of seeing one in the first year or so of Pan-STARRS working. And the answer turns out to be trillions, many trillions, even in a cubic light year, which is not a very big piece of space, needing at least 100 times Earth's iron reserve. So it tells you that this isn't a one planet civilization that's doing this, because there's just not enough material. But it's perfectly okay. If we had a solar system scale civilization, we could produce this many of these solar sails. Because the asteroid main belt contains a million trillion tons of iron. So there's a lot of leeway there. You do have to launch an awful lot, 2,000 a second for 1,000 years. We have no idea whether that's a reasonable number or a crazy number, because we don't know what this interstellar, this pan-solar system or stellar system civilization is like, or what its motivations are. But we can have tests. There's a new telescope being delayed by COVID, of course. New telescope about to open and start operations in Chile, on a mountaintop in Chile, which is much bigger than Pan-STARRS telescope and has an even bigger chunk of sky it can image at any one time. It's called the Vera Rubin Observatory, and it's doing what they call the large-scale survey of space and time, which just means they're taking pictures of the sky, all the sky that's available every night, sometimes twice, two double snapshots, click, click, because that way they can see things moving, in particular asteroids and interstellar asteroids, interstellar objects, we should say, I guess. Estimates are that they will find about one per year. That's not very many, but it's a lot more than we've had so far. And that rate is, of course, a very rough estimate based on one detection. So we will see, and if you get the right number, it will tell us and assume that they're random in space, they're uncontrolled, then it'll tell you how many there are in a given volume of space. Is it really 70 trillion, or is it less, or even more? Okay, those are consequences of uncontrolled derelict spacecraft floating through our solar system. What if instead it was targeted at us, under control in some way, presumably by their computers? So I expect many of you know this wonderful Gauguin painting that's in the Museum of Fine Arts here in Boston. It's called Where Do We Come From? What Are We Doing? Where Are We Going? Well, we can ask the same question, rather less beautifully, of Oumuamua. Where did it come from? How did it get here? And where is it going? Because when it's targeted, all these things have to make sense. So it could come from a normal star, something like the sun, in which case we can look for them because we've got very good surveys of nearby stars now. And it went within, in the past million years, which is a pretty generous amount of time, as you'll see later, it's gone within 6 light years of 4 stars, and that's it. So the only way it could come from another sun-like star is if it was also able to maneuver while in space. But that requires a lot more technology than a simple passive device that is given a push, it went by the star or by lasers when it starts off and then coasts all the way to us. Maybe that's possible, but then that's something you can investigate. How would you do that? What kind of machinery is needed? Could have come from another a star we wouldn't see in a normal optical survey because it's too dark, too cool and faint and small, a lower mass star, a brown dwarf. And that's possible, except we have infrared surveys, which are pretty sensitive, and we can rule out any of them within a degree of the path it came in on. So again, unless it maneuvered, then there aren't any brown dwarfs available. Could have been a bigger star, a more massive star, but in that case, and we don't see it because it's gone. It went supernova in the time between when it was launched and when we saw it. But it certainly wouldn't have been native life. These stars only last for a few tens of millions of years. So even if they've just about managed to produce some life, which seems pretty tough because planets would tend to be still pretty molten after a few million years, then it's super unlikely to be highly technological life. So it could have been that there was a massive star there. A spacecraft was launched from some other star and went shooting around a slingshot maneuver around this great big star in order to correct its course towards us. And this is, of course, with something we do a lot in exploring the solar system. We send spacecraft around Jupiter, around Venus, around other bodies in order to get into the right orbits. So we could test these things. If there's been a supernova, then there might be traces of unusual isotopes in asteroid rocks, and we're about to get back some samples from the surface of a couple of asteroids, which will be our first chance to do this with rocks that haven't been heated coming in through the atmosphere. That may tell us something quite different. Or we could look for the remnants. This picture on the left is an expanding shell of hot gas at millions of degrees. It's glowing in X-rays, and this is an X-ray image in false color, of course, taken by the Chandra X-ray Observatory, which I worked for a long time. And there should be a similar shell of hot gas, and it will be in the opposite direction by now. It was moving. This gas from supernova moves faster than the Oumuamua, so that gas would have gone past us, and the right place to look is exactly opposite to the direction of Oumuamua. Could also leave behind a neutron star, which that little white dot in the center of that image, that's probably the neutron star created when this big massive star exploded. But the neutron stars often get a kick when they're born in supernovae, because it doesn't perfectly symmetrical spherical collapse. If it's just slightly off from being perfectly round, then the little neutron star gets a kick off in another direction and can move a long way. So we can actually be surprised where they, oops, sorry, something going on here. You know what? There we go. So if it's not a normal star, it could be a weird star that was used as a slingshot, because weird stars are not likely to have planets around them which are habitable. And the statistics turn out that finding one in about the right location is plausible. You have to be lucky, but then that's what we're talking about, a single event, and you can always invoke the tooth fairy if you want to be lucky. So the two possibilities: a neutron star, which I already mentioned. There aren't any candidates we know of, but as I said, it could have moved a long way by now. So search harder. We would look probably in the extreme ultraviolet, which is a very neglected band of the spectrum in astronomy, because you can't see very far, but you can certainly see far enough to find a host, a neutron star that this Oumuamua would have come around. Or of course, a black hole. There, you really have to be careful not to get too close. If you want to get a nice strong slingshot, you want to get very close. If you get too close, however, it will rip your delicate solar sail into pieces by tidal forces. So that's not very easy to do. It might be actually not doable, it might be theoretically impossible. So some good calculations for people to do there. Okay, how did it get here? Well, this is where reliability engineering comes in. It must have taken at least 100,000 years, been in interstellar space for at least 100,000 years to get from one star to another. That's 20 times older than the pyramids, 1,000 times older than the Iron Bridge, one of the earliest industrial products still with us, and 4,000 times older than the oldest working spacecraft, the Voyagers. Now, if you want to ensure that you have a 99% chance of lasting 100,000 years, then the reliability engineering tells us you have to plan for a lifetime that is 5 times longer, so about 500,000 years. That is a bit daunting. Is there anything that reliable, right? We've talked about 4,000 times older than our oldest working spacecraft. Well, we'd like nuclear waste storage to be that good because that's the kind of time scale we have to worry about, maybe a little less. You're all familiar, I think, with The Clock of the Long Now by Danny Hillis. It's got a design life of 10,000 years. That's pretty good because now we're only 10 times short of the required lifetime, right? And there may be lessons from that design that we could adopt and see if they can be adopted for spacecraft. And then, as I think George mentioned, there's the ARCH project billion-year library. Can we store anything for that huge amount of time? And remember, we're in a very low mass object in interstellar space where there are fast-moving dust particles hitting the spacecraft and any information storage device, and very high energy cosmic rays moving through the whole spacecraft, which could cause a lot of problems over a long time scale. So it's going to be challenging to see if there's any solution that works, but it is at least something you can start thinking about and calculating. There's another question of how it got here, which is, can you find any material that's stable enough to last that length of time, 100,000 years? So obviously you'd use the hardest bonds, the strongest chemical bonds known. So diamond is one of those. Diamond is, however, an example of what you wouldn't use, most likely. We can make thin sheets of diamond. There's a guy at the Naval Research Lab who was making little ones about this big, and I had one once, but it was very delicate. But if you heat diamond, it turns to graphite because it's a lower energy state. It's not a stable, diamonds are not stable. Also, if you hit them with high energy radiation, they also diamonds turn to graphite then. And both of those are going to happen in its journey from whatever star it came from to us. So there's a lot of work you could do here. One is simply take diamonds and other strong bonded materials and expose them to interstellar conditions, which could be done in the lab, and see if how long they last. And we search to see if we can find any material that might be strong enough to last 100,000 years. Really 500,000 years if you want a good chance of success rather than a 50-50 chance. So another part of coming here is, why did it come here? So remember, it must have left at least 100,000 years ago. At that time, humans were just on their last emergence from Africa. So there would have been no detectable human activity, no technological activity to look for 100,000 years ago. There would have been plenty of evidence for life, so that it's possible that that they saw that this was a promising planet for emerging technologies, or maybe maybe just they wanted to get a close-up view of a planet with lots of life. Or if it was just lucky that they sent it to us saying, well, here's a planet that might get some technology. We were just very lucky to have intercepted it when we did have the technology, within, in fact, a year or so of implementing that technology. It suggests that Oumuamua can't be the only one of its kind. There should be a lot more coming from the same direction. So again, the test would be, what does this Rubin Observatory find, and are they all coming from the same place? So finally, I guess, where is it going? We might actually know that. It's going very close to a red dwarf star called Ross 248. Passes only 1.5 light years from Ross 248 in a trivial amount of time, a mere less than 30,000 years. Nothing. To intercept Ross 248, it would need to make a course correction. So it would need to accelerate one more time, at least. So we could ask, is this really where it's going? So how would we find out? Well, there ought to be planets around Ross 248 if it's an interesting location to go to, and perhaps habitable zone planets. So maybe that's, if we look and there are none, it doesn't make it a very likely destination. It's a mere chance that it's going in this direction. Or of course, we could go to Oumuamua again and see if its course has changed. The right time to change course is as early as possible, because it's a smaller angle you have to move through. Of course, instead of Ross 248, it might be going to another neutron star or black hole, that we still haven't found. Now, that's invoking the tooth fairy twice, right? We need one to bring it in the right direction and one to find it where it should go. And invoking the tooth fairy twice is considered a no-no. It's not impossible, but you're asking a small chance times a small chance. We'd like something better. So obviously, once again, look deeper for neutron stars, and perhaps only in the direction it's headed. And follow all new interstellar objects that will be found by the Rubin Observatory to see if they change course. And maybe with the James Webb Space Telescope, we'll be able to track them for a little bit longer than we can right now. Of course, what we really need is a much bigger telescope. But that's the answer of an astronomer to absolutely every question we ask. Of course we want. I ask now, how is an astronomer like the famed poet and polymath Johann Wolfgang von Goethe? And the answer is, on our deathbeds, we shall all be saying, more light. It is said that Goethe just wanted the windows open, but anyway. Okay. So that's the whole list of possible scenarios that I've just related to you in a much less digestible form, I rather think. But what the point of it is that there's a lot of specific things you can do just by saying, well, okay, it might be aliens. It's not impossible because we know advanced technology civilizations with about this capability exist, because here we are. So what would that imply? And there are lots of possibilities. You might wonder what my favorite is. And so I will confess up, I really like the idea of the accidental messaging, where they're just sending trash out into the universe as part of their transit system and didn't realize they were sending a message. But you'll notice a recurring theme that one of the best things you can do is just go to Oumuamua and see what it's like. It will be obvious if it's an alien craft. So in the whole tree of possibilities here can be ruled out if it's not, right? And then you can get into more details. Does it have identifying marks or not, and things like that? Is it capable? Has it changed course? All these things can be answered once you've gone to Oumuamua, right? Since it's way beyond the reach of our telescopes by now, and rockets, no one's started to even build such a rocket and a spacecraft to do this, you might think we've missed the chance. But there's several ideas about how we might go there. One of them is the Lyra mission, which has just been proposed. They think they know that they could intercept Oumuamua in 2050, early 2050. This is the path it would take in a plan view. In fact, it dips well below the plane of the solar system at one of these points. It does a number of flybys of different planets, starting launch in 2028. It goes past Earth and Venus and Earth again. And then the big maneuver comes when it goes past Jupiter in 2032. And then you wait for it to arrive at Oumuamua in 2050, presumably doing some nice interstellar measurements of on the way, but basically waiting to get photographs of Oumuamua. It does zip by rather fast, going 18 kilometers a second. So you probably have a minute or two where you have good, at most, where you have good imaging, but that could be enough. If it's obviously a solar sail, it's going to be enough. You can carry about a human's worth of payload. A human would be a rather poor use of payload mass, but I wonder what instruments it should carry. What are the telltale, apart from just a camera and maybe a telescope, what would be the right thing to send? I don't know. It's an interesting question. I don't think it's really been addressed yet. Funding, well, NASA could do this in principle, but Elon and Jeff Bezos both have nice big new rockets they'll want to use and show off, and maybe they'd like to just do this for the fun of it, and maybe they'll both do it and see who gets there first and who has the best pictures, and so on. It's not easy being a billionaire. There's so much competition. Another possibility is to use the very idea that started this idea of Oumuamua being a solar sail or light sail, and with Project Starshot, which is intending, as I said, to send hundreds, if not thousands, of small spacecraft past to Alpha Centauri, the nearest star, a mere 4 light years away. But they could practice early on by sending things at very high speed to a more local target, Oumuamua. Because there's swarms of cameras, and that means you get, although they'd be moving much faster, with many of them, you could accumulate more images from more directions. You would also send them in not quite the right direction, send some that are going to where Oumuamua would be if it had changed course to go to Ross 248. So you can search for trajectory changes, which you won't be able to do with this big spacecraft. You'll just go past where Oumuamua should have been and go, dang, it's not there. It's moved. So then you would know, I guess, that it had to change its trajectory somehow, but you wouldn't know where to. These Starshot style cameras would get there really fast. I don't know how fast, but they could be moving at a good fraction of the speed of light, at least 1% of the speed of light. So something like that. That's so much faster than any spacecraft. It would probably be at least 10 times quicker. So instead of 30 years, it might be 3 years. I'm guessing there we'd have to do the numbers properly. Just the detail that we haven't built any of these Gossamer spacecraft. We don't have any high power lasers to fire them off, and permission to fire a very powerful laser from anywhere on Earth through all our working satellites around the Earth, and promise you'll do no harm, that could be difficult to get permission. So both of these are very interesting approaches, and why not both, if it's such an important question? So, there we go. So just before I end, I would give a note of caution. I've been going on about all the possibilities if Oumuamua is an alien craft, and neglected all those astrophysical possibilities. And really, it's only been 5 years, and it can take decades to solve one of these problems in astronomy. A new problem does not get solved overnight, and it could well be that the ingenuity of astronomers will come up with some perfectly good way in which which would explain everything, and it has nothing to do with aliens. So I'm not going to say I'm a great alien believer. I just want to saying that it's aliens does not stop the science. You can still think about the problem in an analytic way and make tests. And so I'm going to end with that, and thank you very much for listening. And oh, look, I've written a book. I've also written the article about this, which if you want to go to the International Journal of Astrobiology, you may be able to download. I don't know. Possibly not. It may be behind a paywall. But it is on Archive, which if anyone knows Archive, you can get that put that number down, or just search for my name and Oumuamua. There's only one such. So thank you very much.
All right, Martin, thank you very much. That was quite a journey.
Yeah, man,
and
really nice.
yeah, so Kim, what was the first thing that popped into your head that you'd like to ask Martin about?
Well, there are a couple of them. One is why, and one of the last thing I was thinking about is what's the business model for this, and what do we achieve by going out and hopefully finding it? And as you said, maybe there's a rest stop somewhere along the way, and we just zip right by it before it gets there. So what's the business model for it?
Well, it's not to make a profit, but it might be to know that there are aliens out there, and thereby we are forewarned if they're bad guys. Because in science fiction, it's always bad. The Borg or something wants to take over the whole galaxy. You know, conquering the galaxy seems to be the thing to do, and we would like not to be part of that. Thank you. So I guess it's a survival thing, not a business model thing. You aren't going to make money off it.
Well, survival. Where does that come in play with global warming? Assuming that we're going to be here.
That's another thing we have to deal with. Yes. The amount of money you that our billionaires would put into such a mission is really very small compared with the kind of investments we need to deal with global warming. Where there is, however, a business case, right? There's plenty of money to be made off revamping our entire civilization to run on electricity. So that's fine. That'll work. Yeah. If we can't solve that, of course, I don't think we'd be too worried about aliens. So.
Yeah, and a follow-up question, Martin. I guess it sounds like there are technical challenges for any of these options. You know, we're already sort of looking at ways of exploring space and finding out more. Bigger telescopes, new technologies is kind of on the cusp of our efforts to understand more about the universe. And so it sounds like even if we put together some mission to go out and find it and explore, we're going to learn something even if we can't answer the big question, right? If we miss it, or if we don't find definitive evidence one way or the other, that technical process of doing this kind of a mission would provide some benefits in terms of what we learn in the process.
Another option is which ESA I think is investigating, and is to build, since we expect now to find one of these every year, right, for the next 10 years at least, you could build a mission, a generic mission that will go to the next one you can catch up with, and that could well be found more easily than Oumuamua. We may catch it on the inbound, so we might be able to rendezvous with one of these interstellar objects.
Yeah, so get ready to try and catch it next time around, assuming there's another one coming.
There's no next time around.
Yeah.
Martin, could you stop sharing your slides now?
Yes, happily. If I can. There we go.
All right, there we go.
Martin, I do have to say I love the presentation. It's really fun, and it makes you think outside the box. And that was another piece that I came up with, was the out of the box thing. Is how do we think? As a scientist, how do you think about these concepts, not using the tools that we have, kind of thing? So thinking outside the box of things that what can we do, looking at things on Earth that have not been solved, and using those as jumping off points to figure out what this thing is.
I don't know how far out of the box it is. This whole thing it's stuff you are not familiar with, obviously. Why would you be? It'd be a waste of your time. But I'm using mostly ideas that are very common in astronomy and in spacecraft design, but just applying them in a very strange context.
No, I understand that, but I'm wondering the things that, as a scientist, you're looking at or using tools that you have.
Yes. To
try to explain something that is outside of that toolbox.
Something we'd never seen before. Yes.
Yeah.
That's just normal science.
Yeah. And trying to invent new tools to deal with an anomaly. We have an anomaly, it's a mystery, we don't know, and we have to find out how to figure that out.
And one thing that came to mind was the Neanderthals and the stalagmite circles in the caves, and 150,000 years ago. Were they thinking about the future?
Yeah.
Probably not 150,000 years, but.
And I had a question, Martin, about the one of the questions I think that some of us feel helps to sort of frame our sense of isolation from the universe is the Fermi paradox.
Mhm.
You know, if there were civilizations out there, how come we have no evidence of them?
Oh,
And so one of the possibilities is that we would get evidence, right? If we go
yes.
explore this and we found we
Yes.
get evidence. And I'm wondering, given, let's take the analogy of what happened when NASA got out in space and took photographs of the blue planet. And then our dear friend, Stuart Brand, put it on the cover of the Whole Earth catalog as a symbol. And that symbol really changed a lot of people's conceptions about the environment, the fragility of the blue planet, and, helped to sort of fuel a different way of thinking about things. And I'm wondering if you think whether finding evidence that essentially solves the Fermi paradox by saying, well, we have now a sample of two. We found an evidence of civilization. How do you think that might affect people's psychology?
Oh, I think that would be like a Columbus moment for the Europeans going, oh my God, there's a whole world we never knew about, a whole type. Yeah. But how we would react to that is another question. I mean, there'll be a bunch of reactions, but what the overall feeling of our world is, I don't know. Maybe we'll feel scared and we'll want to protect ourselves or something. Somebody had a question.
We have a couple in the one in the chat is about from Roger. Is there any reason why a controlled spacecraft would wobble and not hang around to study us? So that kind of hints at the idea, could this be actually a controlled craft that was just doing a quick flyby and didn't care
I didn't
to hang
say
around?
it, but I think the fact that it's tumbling rather suggests it's not under control. On the other hand, the fact that it accelerated would mean that it had to keep its solar sail oriented at least a good fraction of the time so that it could receive the radiation and not be edge onto the sun. So that would imply some control of orientation, but I don't know. I find it less convincing than a derelict. Yeah. And the other possibility, of course, is that we're not the target, that we were an accidental place that they went by because Ross 248 is such a great place to go, and we were just a slingshot target ourselves. Mm-hmm. And we're not, that's like a Rendezvous with Rama, the Arthur C. Clarke story, where oh my God, an alien vessel is coming to see us. Oh, what's he going to do? And it just goes on by. We weren't part of it. Doesn't even pay attention to us. It just goes.
We have a question here from James Garrity.
Yes.
Yeah, thanks for the thought-provoking talk, Martin. Can you say a few words about if Project Starshot were to send, craft to Ross 248, let's say, and let's suppose that the craft hypothesis is wrong. Can you say a few words about what the science case for that mission would be, or would this be exclusively? Would you be looking at Ross 248 itself, or
Ross 248
itself?
Ross 248 is further away than Alpha Centauri, so they wouldn't be sending it to that star. You'd be sending out probes in the direction of that star to overtake Oumuamua, and in a cone to sort of cover the bases in case it changed direction.
I think my question is aimed at let's say that you're putting together a proposal for this. It's to that extent. What is the science case? If the craft hypothesis is wrong, what science can you do with a craft like that?
Yes, exactly. You'd want to have you want to know what it's made of. You would take spectra in very many different bands, probably that you can't do very sensitively from Earth, including the infrared. You would probably try to fire a projectile into it and make a cloud of dust to get some idea of its strength. And you would also and then take a spectrum of the material that was blasted off. Especially if you could also, instead of a projectile, you could use a laser beam and that would bring off heated material, which would be much easier to take a spectrum of and tell you the elemental composition.
So primarily about the object itself, then?
Yes, it would have. Yes, because it's still the first interstellar object we found. Is it? And if it's rocks, then what kind of rocks and where did it come from? The implication is then that there are trillions more. So it's telling us something about a component of our galaxy that we didn't know about.
Indeed.
So,
Thank you.
and I would say that the proposal to NASA would be stressing this and mention that, oh, by the way, it might be an alien craft.
And
Martin, I have
we may
another-
have to wait a while for the next one.
Yeah.
Right.
Well, no, about a couple of years. We should get one a year, starting once the Rubin Observatory is operational.
Martin, I want to follow up on your comment about the three-body problem, the science fiction book, and the this unfriendly interstellar civilization that comes visiting. As I remember, it was a while, but they were invited by some activists back on Earth, right? I think that was sort of part of the theory of it. They were invited, or there was some message that was
sending
sent.
out a signal. We intercepted it and sent back a reply. Big mistake. Right.
Yeah.
So I'm very worried about the idea that we should be sending out signals.
Well, I wanted to ask you about that because you mentioned Voyager. If someone out there in far space, comes across Voyager, they're going to be able to identify it. They're going to be able to locate us. And is this, you share a concern about that kind of exposure?
Yes, much more. I could concern about some electromagnetic radio or laser pulse message that's being sent out, because that goes, it only takes a few years to get to the nearest few stars. And that's more dangerous than sending out Voyager, which is going so slowly. It's only just really left the heliopause.
So what about the time scale? Like, as you pointed out, Oumuamua has been in transit for what, 100,000 years or something like that. So that's on the time scale that's well beyond the time scale of if not life itself on a planet, civilization.
Oh, civilization, but not life. No.
Yeah. So how do you? It's like if interstellar distances are so vast, and the time required to transit across those interstellar distances, doesn't that kind of moot the sort of the concern about notifying some other civilization? Because the time required to transit those distances are so high.
Yes, I guess that's where I put a little caveat in and say, well, there could still be new physics that we don't understand. So maybe there really is warp drive, and we just nobody's come here because it wasn't a very interesting place to visit, for instance.
Martin, you mentioned something towards the end, which I loved, which is, well, maybe the astronomers will get there before we do, kind of thing.
Yep.
The thought I had was, what happens if the astronomers get there and they realize that it's an alien spaceship?
Oh, yes.
Yeah, wouldn't it be cool?
Oh, yes, it would.
Yeah.
I think it would be fine. But how are you going to prove it? And that's what the whole point of my thing was, to say, let's see how we would test this.
Yeah.
And
They're on the same track.
Yeah, you also have, I think, it sounds like there's some confidence now with the fact that we've discovered a couple of other interstellar objects. So now we're getting better at finding them, that if it was some kind of alien craft, then that's an indication that there are lots of alien crafts out there, and we'll find some.
Yeah,
we keep looking, we'll find some.
Maybe we can even capture one.
Yeah, and maybe we'll interrogate the little aliens.
Yes, well, yeah. Avi Loeb, by the way, Avi Loeb, I sent this paper to him before I submitted it, and he replied saying, I made his day. It was a very nice paper, rational, so that was good. He recently was quoted as saying he'd love to find a piece of alien technology and just press the buttons to see how it worked.
Oh,
hasn't he seen any movies about this kind of thing? I mean, come on, Avi. That's going to end well, isn't it?
Yeah. So
I would do any playing with alien technology a long way from Earth.
Yeah. The questions now that are being posed in the discussions about Project Lyra and Project Starshot, how do you think it's realistic that we will see something actually begin to take root as an actual
And actually make
mission?
one of these happen. Yeah, I think Starshot's very plausible. They're looking. They will. I know they are looking for intermediate targets before sending things off to Alpha Centauri, just to prove the technology. And I'm sure this would be a dramatic test. And Avi is closely involved with them, so he will be pushing that, I'm sure.
And is that one of those funding? It's not. Explain to me whether that's a sort of a. We've been doing space by government expenditures largely.
Yeah.
Is that still the case with Starshot and with Project Lyra,
At
or
the
are we
moment,
beginning to expand?
Yuri Milner has backed it to $100 million, but that's not expected to be enough money to get the final working gigawatt laser and to send things to Alpha Centauri. But maybe it's enough to do an intermediate test at a much lower power to Oumuamua, and some other solar system destinations.
So true exploration of space, given the resources of time requirements, is still ultimately going to require some governmental involvement and potentially
yes, that's
funding.
not very strange, as in fact talked about in this great book. It's quite normal to have government lead the way on high risk future technology type ventures, and they can invest for the long term and bring the risk down to the point where venture capitalists can then jump on. And the risk is not just financial; it can be technological, it can be legal, it can be all sorts of things.
You see, what's the right now? Is there appetite for governments to fund this kind of very, very long range, long term mission?
It's not dramatically much longer. The Project Lyra, not dramatically much longer than some of the outer planet missions that are planned. People have to plan for 20 or 30 years ahead. Currently, if you want to get to Uranus or Pluto.
So what's the process of getting that kickstarted and getting something actually?
Well, it would have to. The best thing would be if it had already been in the Planetary Decadal Survey, which the report just came out and did not mention. I don't think it mentioned Oumuamua or interstellar asteroids, interstellar objects, as a target of interest.
So it may take some time before that really gets off the ground, so to speak.
Yeah, probably.
Yeah.
Unless you can get a constituency together and to argue for it.
Yeah.
Probably will become more interesting if we start seeing one or maybe more per year from the Rubin Observatory. That would make the whole thing more lively, and people could say, "Oh, yes, so it really is possible to send one," and then they would start to build one, and then it would take a while before it gets launched.
You mentioned in your your preview, I think, when you're talking about your asteroids book, that we're close to getting samples from asteroids back to the Earth.
Yes. Well, Hayabusa 2, the Japanese mission, has already brought back a few grams from their target asteroid. Excuse me. And OSIRIS-REx will be depositing its much larger, we think, sample from Bennu I think it's 2024. And once we get that back, that should be very interesting in many ways, because we've never had a pure, unsolid sample of asteroid material to work with.
Kim, do we?
I was wondering, is there anybody in the audience who has a question you'd like to
please.
throw out?
Yeah.
Raise hands or just unmute. Don't all answer at once.
They're shy.
We may have to go to the bar and get some libation first before people listen up.
I would fire a second one at you, Martin, if you would allow me. So you mentioned you were talking about diamonds and being heated and turned into graphite. I was wondering, what is the expected heating from interstellar travel?
Right.
Do
So
you know that offhand?
the spacecraft itself will be very cold. It will, it could even be at cryogenic temperatures, and that raises whole list of issues. But as it's moving along, it will be hit by interstellar dust particles, a few microns across, moving at very high velocities, and they will heat up and ablate part of the surface of the space of the sail, and probably make little holes in it. And it'll heat up an even bigger area than it actually makes a hole, and that would turn to graphite if it was made of diamond, right? So,
Right, and an embrittlement mechanism is not something that really jives with reliability engineering.
exactly. And so one of the things AbbVie did with Bialy is work out that a sail like this would lose about 50% of its mass in about 100,000 years. And so as astronomers, see, it survives. As an engineer, you say, that's awful, right? Where's my order of magnitude or factors of few safety margin, right? It's a terrible engineering thing if you lose half your spacecraft. What if you're off by a factor of 2 in your estimate of the dust rate? It could well happen.
Or if you hit a dust cloud in the middle somewhere.
Yeah, and plenty of such clouds, I bet, could exist that we'd never detect them currently.
Yeah.
We've got another question here for Roger. Roger, last name, please. And
Yes,
where are you coming in from?
I'm coming from the UK,
Oh gosh, hi there.
and it's
I came from the UK. How did you guess?
quarter to 2 in the morning here.
Oh,
So, but my wisest, I'm not an astronomer and not an engineer, but I haven't understood how the idea of a solar sail is consistent with the measurements of the Oumuamua that we've heard about.
yes, it is consistent. I think we know that Oumuamua is in a very is probably sheet-like construction, right? I'm sticking with the alien craft idea, right? We know it. We know whatever it is. In fact, whether it's a rock or whether it's an alien craft, it has to be either cigar-shaped or like a pancake. Yeah. And if it's going to accelerate, then that pancake has to have a very low mass and a very large area. So it's completely consistent with being a light sail. Yeah.
Sorry, I thought it was about 600 feet long and something about.
It could be that big. Yes, it's in 100, 200 meters, so 300, 600 feet.
Okay,
Something
I
like
thought
that. Yeah, and that in both dimensions.
right. Okay,
But less than a millimeter thick if it's going to be accelerated by sunlight.
okay. Thank you.
Yes.
And Martin, could that acceleration have been kind of an accidental? It just happened to get itself into that position and got pushed
That
if it was a
is something-
derelict?
Well, we have some information about how it was tumbling, and the right thing to do is to model that and see how much of an impact of an acceleration it would get. It would only be a fraction of what you would get if you assumed it was perfectly under control, right, and pointing perfectly in the right direction.
Yeah.
And I don't think anyone has modeled that yet, so I think that would be another investigation to work on.
Lots to think about. So I think we
George,
should probably, yes.
Did you tell Martin about going down to the bar?
I mentioned it. I think it's time now. So why don't we turn it
I
over to Jennifer, and then we'll have a closing, and then we'll go to the bar.
Excellent.
Wonderful. Okay, thank you very much. Yes, so as George mentioned, we do have a tradition here at Long Now Boston when we were doing in-person events. Some of you may have seen the slides at the beginning where we were in the Venture Cafe at the Cambridge Innovation Center, and there's a bar downstairs. And so after the event, we would all convene at the bar and kind of discuss this further. So we have a equivalent of that virtually where we hang around after the formal event this evening. Before we go to the bar, I really want to thank you, Martin, very much.